Everyone. So yeah, let's talk about assignments and projects real quick. So homework 5 is due tomorrow at 9 p.m. and not today, and that's because we were a day late on releasing it. So we gave everyone an extra day. So it's due tomorrow, but we're still releasing homework project 2 on time. And so this is the project 2 instructions. This is on the GitHub, and I'll do like a formal Piazza announcement after this lecture if it's not up there already. So essentially, for this one, it's not a Kaggle competition, but rather we're going to give you the movie lens data set, which is the same kind of Netflix problem data set that we talked about during that lecture, that latent matrix factorization, whatever, that lecture. So this is a kind of a modified version of that data set to be a little bit smaller so that it's a bit more tractable. But it is like 1,500 movies and something like 1,000 user ratings on those movies. And based on that, you're going to be generating visualizations. So I went through and I updated the data set so that all the movies are from after the year 2000, because I think the previous data set had like 1970s all the way up to the 1990s, and I didn't recognize most of the movies on that list. So I went ahead and updated the data set. Again, so for each movie, you have like a unique ID for the movie, the title of the movie, as well as some tags. So some broad categories about what genre each movie is in. And then we also have the ratings. So we have each user, each movie ID, and what rating they give it. And so the report's actually going to walk you through exactly what you have to do. You do some basic histogram visualizations of the ratings or the actual data itself. And then you're going to train like that SVD-like matrix factorization model on this data. And then you're going to generate some new visualizations based on that. Kind of like how during lecture I said, like you can put them on axes, and on the latent factors you can say this is more like this is more like that. These two movies are opposite each other. That's kind of what we're going for here. There's also a PowerPoint presentation with like a guide. I haven't opened this yet, so I don't know what's in there, but I think that's going to be useful. And then let me see. And then here's the data. So even in the movies, you can open this up and you can see, these are all the different kind of movies. I sorted them in alphabetical order for just kind of arbitrarily. But hopefully you recognize some of these names. And then for each one, again, we have kind of the one-hot encoded genres for each movie. And so that should be enough to get you going for getting that SVD-like model trained. So yeah, this will be fun. So again, it's not a competition per se. There's no like performance metric that you're competing on. But you do get to post your visualizations on Piazza afterwards, and whoever has the coolest visualization gets extra credit points or something like that, right? So this is kind of your chance to kind of explore that space, see what's possible, and go from there. Sound good? Any questions about homework 5 or project 2? Okay, project 2, again, the visualization is due next Tuesday, and then the report is due on the Wednesday after that. So kind of the same structure as the Kaggle. Okay. All right, then let's move on with the lecture. Okay, so today's lecture is on probabilistic models, which is really interesting because when I learned machine learning and in the course that I took, we actually started with probabilistic models, and then we kind of made our way into linear regression. So this course is structured kind of in the opposite way. There's no right way to do it, obviously. Machine learning is such a broad field with so many different facets that as you can kind of look at it from all these kind of different perspectives and still make it to the end. But today we're going to be talking about probabilistic models. We've already talked about probabilistic models before in the previous lecture when we were talking about embeddings. And that's, again, because we have this kind of chicken and egg problem where it's kind of hard to talk about one without talking about the other. So we even talked about like first order Markov assumptions during the last lecture. But we're going to really get into it today. And then also the next 2 lectures are dedicated to just hidden Markov models, which is one kind of common example of a probabilistic model. So this will kind of set everything up. This is kind of going over the basics of what a probabilistic model is, what a generative model is, and all the kind of basic nomenclature and the language that we need to speak, including a lot of probability and a lot of things about probability. And then after that, we'll kind of talk about hidden Markov models, talk about dynamic programming, talk about sequence to sequence, more kind of application more fun stuff. Okay, so far in this course, we've kind of talked about machine learning in these sections, right? So we have supervised learning, where we give you some input X and you have to predict some Y, right, to the best of your ability. And then we also have unsupervised learning, which is more clustering, where you don't have labels and you just have the data and you're trying to kind of represent that data in some low-dimensional space that makes semantic sense, and that gives you also a lower so you're extracting the structure out of the data, right? So for the remainder of this course, this line becomes a lot fuzzier. So when we talk about things, we're still going to structure them in a supervised way to start. We're still going to say there's some Y, there's some X, and you're trying to predict Y from X. But this line becomes a lot more blurred because we're not really, it gets a lot harder to start labeling things as labels or input data or supervised or unsupervised, right? Even within the past couple lectures, when we were talking about latent factor models and such, that wasn't even unsupervised per se. It's not that you didn't have labels; it's that you only had labels and you didn't have any features, right? So we're starting to see how all these different kind of areas blur together, and everything's kind of everything else. So we're not going to do this distinction anymore. And instead, we're just going to say that we're optimizing some metric, right? We're optimizing some loss function, whether that's structured in a supervised classification way, then that's fine. But we're just going to be talking about optimizing some general loss function. And then as we talk about probabilistic modeling, which is in that square, and it is placed under supervised learning because that's the easiest way to talk about it in the kind of structure of supervised learning, but we'll quickly see how that kind of decomposes and like devolves, and we can't really talk about that in that way anymore. Yeah. Okay. So so today we're going to talk about some basic probabilistic models, including naive Bayes, and then from that estimation and sampling. And then after that, we're going to have a brief overview of some advanced probabilistic models, just to see what's possible using this probabilistic model framework and this generative model framework. And then, like I said before, the next couple lectures will really dive into hidden Markov models to see how we can apply that. And then there's also a probability recitation on Wednesday, and kind of the litmus test as to whether you should go there or not is I'm going to go through a lot of probability equations, and if you kind of find yourself losing the thread or kind of not understanding how I made the jump from one to the next, you might want to go to the probability recitation just to kind of brush up, right? Okay, so we're going to start by kind of defining a probabilistic model. And so we also call these kind of models generative models, and we'll kind of see why as we move on. But probabilistic models model a joint distribution of x and y. So this probability of x comma y. And this is different from what we saw in the previous lecture, right, where we had x conditioned on y. But a probabilistic model actually models this entire joint distribution of seeing x and y, observing x and y at the same time. So once we have this joint distribution, right, and by the way, if this is kind of confusing or not, if it's too abstract, you can always think about this in a supervised way, where we say we have some input x and some target y, and the model is just modeling the probability that this some input and some output is observed together, right? So if you need to put in that framework for now, that's totally fine. And then if we have this joint distribution modeled, then we can use that to make predictions. And here we have, so is everyone here at least has seen Bayes' rule before? Raise your hand if you've seen Bayes' rule before. Okay, cool. I'm assuming some probability background. So if we have this joint distribution modeled, if we understand that distribution fully, then we can, whenever we have to actually do a classification task, which is more what we're used to, right? What is the probability of y given some input x? We can just use the definition of conditional probability, which is the probability of x comma y over probability of x, and we can make that prediction as long as we have some model of p x comma y. And then we can take that one step further via Bayes' rule, and we can redefine that further as that other statement. We're not going to pay too much attention to that right now. It becomes a lot more important later. But for now, we're just understanding that if we have p x comma y, we can do normal inference with it, as we would before. And then also, if we have p x comma y completely modeled, we can infer marginal distributions as well by marginalizing out whichever variable we want to marginalize out, right? So if we want to know the probability of just observing y on its own, we can always sum over all of the x's to get that probability, and vice versa. Same thing for p, probability of observing some x. So the point that I'm trying to get to is that if we can learn p x comma y, if we can learn or model that full joint distribution, we can do a lot of other things with it, right? And it becomes very useful. So just to kind of put this in a more concrete way, let's see an example. So we have x and y. Let's say y is spam or not. Spam or ham is another common name for it, but we're trying to determine if an email is a spam or not, right? So we have this y variable, spam or not. And then let's say the x variable is what word exists in that email, right? Whether a word exists in that email. So let's assume that this is our complete problem space, right? So the only 3 words in the English language are help, homework, and winner, right? And that email can either be spam or not. So setting that this joint distribution sums to 1, which makes sense, right? We want all the probabilities to sum to 1. And given that we have this complete model of this joint distribution, right? We have this joint distribution completely defined. What is the probability that some observed x is homework? You can shout it out. 0.5, right? Yes, you just add them together, right? So again, we can think of them as just adding it. You can think of it as just marginalizing out the y, right? Yeah, I'm not going to talk more about that. That's pretty straightforward. Another example, and we're just kind of establishing that having this joint distribution is useful. What is the probability of y being spam given that the email is the word help? And so we can use the definition of the conditional probability down here, right? So you just plug in the numbers, and I won't wait for a response. The answer is 0.6, right? Because the joint probability of this is 0.15, and that's just the lookup table, right? We have this encode, we have this learned already. We're assuming that we have some learned model already, right? And then you have this, the bottom part here again is just what we had before, and we can divide it and make this prediction. All right, finally, so far, right? This is just the probability of observing a variable, and then this is kind of the typical. If an email is help, what's the odds that it's spam? But if you have this joint distribution, again, you can do some interesting things that we haven't been able to do before or we haven't seen before, which is if conditioned on the fact that the email is not spam, right? What is the probability that the email's word is help, right? So note that this is flipped, right? This is not what we've seen before. Typically, we've seen p of x, maybe even p of y, or p of y conditioned on some x, given some input, what is the output? But we haven't really seen what is the input given some output, right? And this is what I mean when I say it kind of loses, the label input correlation starts to lose a little bit of meaning, because just given any 2 variables with the joint distribution, we can just do this kind of exercise, because it's all just probability, right? It's all just probability definitions. So again, here, because we have this joint distribution, we just look at p help comma not, which is 0.1. You just look it up on the table, and then the bottom part, it's conditioned on y. So again, the denominator, you just look it up, and it's 0.6, or you add them up, right? You add up all the y naughts across x. You marginalize x out, and you get 0.6 on the bottom. All right, do those examples make sense? It's pretty straightforward probability so far, right? Any questions? Okay, cool, thanks. I appreciate the thumbs up, by the way. That's like a very clear, like, got it, move on, thank you. All right, okay, so now we have to talk about training. So how do we get this table on the right? The goal here is to learn this joint distribution So the objective function here is just maximum likelihood, right? So given some observations, we want to maximize. Again, this is just MLE, right? We're just maximizing the likelihood, and then again, as always, you can rearrange that into minimizing the negative log likelihood because we like dealing with that more than dealing with this directly. So it turns out that the ideal way of doing this is just to do frequency counts. So given some data set, right, of X and Y pairs, right, turns out that the solution for maximizing this likelihood is just to count how many times each pair occurs, right? So you can imagine in some data set, we have some pairs of help, homework, and winner, and spam or not. And you can imagine that if the pair, I don't know, help and spam occurs a lot, if there's a lot of those in my data set, then that joint probability is higher. So we can just count the occurrences of each example in our data set, and that becomes our model, right? Our model is this lookup table where we define the probability for every single possible pair. Yeah, I should point out this only works because we're assuming that it's like independent sampling, right? An independent IID, given the IID assumption, which doesn't hold up in the real world, but again, for now, it's kind of like assume that the friction is 0 in like physics question, right? We're assuming IID here for everything. Okay. So the interpretation of this is just to kind of talk about this at a higher level. Given some model structure, we're just finding the parameterization that best explains that data. It just happens so that our given model structure is fully defining this joint distribution, which in our case we do by defining this lookup table. Okay, all right. Okay, so we can actually prove this. So you might, so it's weird because like intuitively that makes sense, right? You just count the occurrence of everything in your data set and that becomes your lines on the lookup table. But we can actually prove that that actually does in fact maximize the likelihood as defined on this slide. And so that's what this next slide is going to be. So if we reparameterize that lookup table as that equation up there, where W is just like weights, right? But weights are like examples in your lookup table. So we're just doing that out of convenience, that first line. We can actually prove this without doing this reparameterization, but doing this makes our lives a lot easier. Okay, so we're just going to redefine that model, which is our joint distribution, as that equation up top. And then if we insert that, if we replace that into that minimum log likelihood formulation we had at the bottom here, we end up with this, right? So we're just replacing P with whatever we came up with here, and then we're splitting it out to those two terms. Then, if we calculate the gradient of that term with respect to some data point, right? And then we for some optimal solution, right? And so the gradient at the optimal solution is 0, right? So we're going to set this to 0. And so we end up with this equality, where we say, again, the W that minimizes the log likelihood is in fact the ratio of the number of observations of that specific pair compared to the number of data points in your data set. Okay, so this is just a really, again, so this is kind of proving the intuition that the frequency of the pair in the training set does in fact maximize the likelihood, right? But this is just kind of a formality of doing it. I think intuitively it already makes sense, but just to prove that it actually does maximize the likelihood. That's what this slide is. Yeah, this won't be on the homework or on the exams or anything. It's just we're just kind of convincing you that in fact we can count just the frequencies, and that's good enough, or not good enough, but that is the optimal solution for this specific model setup. Okay, so as you might imagine, this is this kind of a model where we just have a lookup table composed of the frequency counts of our data set overfits really hard, right? So if you have a really small data set, even if you sample independently, like well from your held out set, if your data set is small, you might not really capture that very well. So it's going to completely overfit. So what you can do, and one of the popular ways of regularizing these kind of models is to hallucinate data or add kind of pseudo counts into your data set. So this isn't actual observed data, we're just pretending that we did in order to add a little bit of regularization to our model. And so instead of just the data counts and like the total number of data counts, we're just going to add arbitrary data at the top and add that count to the bottom. And this actually is pretty commonly just a uniform distribution. If you have some known prior, you can kind of insert that as well, but most of the time it's just like a uniform distribution of all the data sets, right? So we're just adding this term at some lambda so that our model doesn't overfit as much. We're almost smoothing it out, if you might imagine it that way. And we'll kind of talk about this later on in the slides as well. Okay. But yeah, so we're just adding pseudo data, fake data, so that the model doesn't immediately overfit to the data set that you gave it. We're kind of smoothing it out a little bit with this lambda function. Any questions about the model so far? It's just a lookup table where each line is the frequency of each pair observed in the data set. That defines our joint distribution, and then with that joint distribution, we can do a lot of useful things. That's kind of the takeaway. Okay, so we call this a generative model, and everything else that we've done, including logistic regression, we call discriminative. So a generative model models both at y and x, right? It models that full joint distribution, which means we can do a lot more useful things with it. And we saw some of that already. Whereas in a discriminative model, we model y given x, right? So it's only modeling y condition, the probability of y conditioned on x, right? So there's possibly less things that we can do with that. So yeah, okay. So the next slides, let's talk about the benefits and drawbacks and why you might want to do one over the other. So for a generative case, we model all of this joint distribution p x comma y. And because we're doing this prediction via Bayes rule, it actually can tolerate missing data. So what we mean by missing data is because we already have this probability distribution completely mapped out, even if I say, what's the probability of y without giving you an x, the model can give you back an answer, right? Because we just marginalize x out. So it can actually tell you the probability of y, right? Or just the probability of x. It doesn't need an input, right? Whereas in logistic regression, or rather in a discriminative model, because it's only modeling the probability of y conditioned on x, if x is missing, if x doesn't exist, then it can't tell you anything, right? It requires that input. It requires whatever you conditioned on. So yeah, because it directly models this prediction task, it can't naturally tolerate missing data. I'm just making sure I'm not missing anything here. Nope, cool. However, if that's all you care about, so if probability of y given x, which is like your prediction task, if that's all you care about, then a discriminative model does always, not always, like the majority of the time it does better. And the reason for that is because it's directly learning that task, right? So if all I care about is x is always going to exist no matter what, and all I want to do is predict y to the best accuracy, to the best of my ability, then a discriminative model learns that directly and actually minimizes the log loss. So the optimization parameter, or the goal of the optimization itself, is to do that task the best possible, with the best possible performance, or with the least possible loss, right? Whereas in a generative model, it's combining these multiple estimated values. So it's kind of indirectly learning this prediction task of predicting y given x, right? So because of that, it's going to try its best to model x comma y, and it's going to try its best to model probability of x, but there's no guarantee that the probability of y given x from that is going to be the best possible performance or the best possible accuracy. Yeah.
Can you think about it like the generative model is like a form of regularization of the discriminative model, though? Because you're learning over like a wider data set, so you're not going to fit as well to specifically the task you're trying to. But like maybe there's like a more direct way, but yeah.
Sure. Yeah, you can definitely get to discriminative models from generative models, right? Like discriminative model. So I'm thinking back now because that's how I learned it. Is I started with generative models, and then you can make some assumptions about it, and then you kind of end up at discriminative models. I wouldn't say it's regularization per se. I think you're more latching on to the fact that because we're modeling the entire data, right? Like theoretically, that might be better generalization because you understand like everything about the data and not just the specific learning test that you're trying to do, right? So not really regularization, but I get the point that you're making. Yeah, and actually, I think I have a slide on that in the next couple slides. Yeah. Okay. So yeah, so the point of the slide is saying discriminative models do better on the actual prediction task because the generative model, it doesn't really care, right? It only cares about modeling the best joint probability. So it doesn't. The training objective of generative models doesn't per se maximize accuracy. Okay, so just to kind of talk further about what I said about generative models, kind of fully understanding this joint probability distribution, we can actually generate more samples from this learned model now, right? Which is kind of where generative models come from. Wherein because we have completely specified this probability distribution of x comma y, whatever we can actually sample data points from that model, and that newly sampled data set will have the exact same kind of statistical properties as the original training set that you trained the model with, right? Because it's fully characterized the data set. So this is kind of like a pseudocode example of how you would sample data from p x comma y, given that like spam or ham example, where you would just sample some random number between 0 and 1, and if that number is below 0.15, then it's this example, right? And if not, then it's this example after. It says 0.25 here, but it's just a lazy way of saying greater than 0.15 but less than 0.25, right? Because it's cumulative. But anyway, so it's pretty straightforward to sample a completely new data set from this joint probability distribution. Okay, and then I mentioned before that generative models can tolerate missing values because the model already understands the probability of the missing value itself, right? So like I said, because it has already modeled what x looks like, even if I say probability of y not given any x, it can do that, right? Because it can just marginalize x out. Whereas, as I mentioned before, it's a little repetitive. Discriminative models can't do that because it's only modeled y conditioned on x. So kind of going back to the point that you made, and I will mention that this is a fairly contentious point, which is that some consider generative models to be more elegant or more kind of comprehensive, right? Because it tells the complete story about the data that you give it, right? So you're not just trying to optimize performance on whatever task that you're trying to do. It understands the data better because it's learning this joint probability space, and so you can really mess with it. So it's in fact it's really useful if you can't decide what the prediction task is before you train the model, right? So in this case we had this really simple example of spam or not, where you have these two variables. In our understanding, it's pretty obvious that spam or not should be conditioned on the input variable, right? So that's how we're going to use it. But it's possible that your data set just has a bunch of variables and you don't actually know what you want to do. You don't know what you want to predict based on what else. You don't know what makes sense, what doesn't make sense. And so you can just train them all on your data set first, and then you can decide what your actual prediction task is going to be afterwards. Yeah? Yes, that is the rest of the lecture. Yeah, no problem. It's the next 2 lectures and a half. Yes. Okay. Let me make sure I covered everything here. Yes. Okay. Any questions so far? Yes. Correct. Right. So here we're assuming that this is like a good representation, right? So we're assuming that this has understood everything there is to understand about the data set, about the training data set. So sampling will give you a new data set that is statistically identical to your training data set. If your training data set is not an accurate representation of the true problem, then this won't be either, right? But you can clone whatever your data set you trained it with, essentially. Yeah. Mm-hmm. Any other questions? Cool. All right, let's move on to naive Bayes. So let me see how to talk about this. Okay, so a lot of you, as we talk about this kind of probability model, where this probability model is just a table of every single possibility, right? So, if as we go through this, you might have already realized there are some problems with doing this. And so now the question is, how can we structure our model in a way that we don't run into the problems that you might have kind of inferred throughout these first few slides? So let's go through that. Okay, so, and just to set this problem up, because we need to be able to talk about this in kind of a rational way, we're just going to structure this. We're going to structure this. We're just going to structure this in a supervised way again. We're going to start in a supervised learning, and then we're going to take that away eventually. So again, let's assume that we have some single y. So this is spam or not. It could be binary. And then we have some vector x that's d-dimensional. So in the simplest case, let's just assume that it's 1 hot, right? So the dth value, the x at position d is just 0 or 1, right? So we just have a binary vector. And so the goal is to model p x comma y. And this is the same thing that we've talked about before. So just to show the example again, this is the same exact thing that we had with spam or not, except with winner and homework, right? Except these columns are binary now instead of having like the strings inside. That's all this is. So as I kind of alluded to before, you might notice that this model complexity is exponential with respect to the length of x, right? So the more feature columns you have in your x, this model grows exponentially, because not only do you need to add those columns, you need to cover every single possible combination. So it becomes 2 to the d, right? Where, is it 2 to the d or is it d squared? No, it's 2 to the d, right? Because if you have 1 column, it's just per y, you only get 2. But if you have 2 columns, you get 4, 8, 16, 32, etc., which is like the worst possible complexity for a model that you could possibly have, right? So clearly, writing down our entire joint probability distribution into a lookup table might not be the best idea, right? So how can we structure our model in a way that's not a lookup table, such that we can kind of still capture this distribution, but with less parameters, right? And as with other problems that we've discussed before, we do this by making an assumption, and that is the naive Bayes assumption. So there's a lot on this slide. We're going to walk through everything. And this graphical model diagram on the right here is actually quite important, and that's going to pop up constantly throughout the rest of this lecture, as well as we talk about HMMs. So we're just going to take our time on this slide and really walk through everything here. So in a naive Bayes formulation, we have this generating model. We have some single y, right? And we're going to store, the model's going to store first the distribution of y, right? So probability of y being 1 and the probability of y being 0, right? Just kind of on its own. That's the first thing we're going to store. And so that's what's represented by that white circle y there. The color of the circles are also important as we kind of go through this graphical model diagram, okay? So conditioned on some y, of which we're going to store like the distribution of, we're now going to keep track of the probability of each x conditioned on y. And that's what these arrows are, right? So these are the dimensions. So this is the x vector, right? But each element of this x vector is only going to be conditioned on this y, right? So kind of interpreting that further, what does that mean? We're saying that each x is conditionally independent given some y, right? So we're saying these x's don't have anything to do with each other. We can completely model each x given just by conditioning it just on y. And this is what the naive Bayes assumption is. This is what the naive independence assumption is, right? We're saying that the x's don't interact with each other at all. Each x is just conditioned on some y, right? And again, you might notice that this is flipped, right? So I thought before we were saying spam and ham and the words in my email and whatnot. So kind of thinking in the discriminative model kind of a way, kind of a framework, we would say, why wouldn't you just store y given x, right? And that's certainly what a discriminative model seeks to learn. But in this case, in this generative model, in this naive Bayes model, we're going to keep track of, again, p of y and p of each x given y. So that's each of these arrows, right? So the first model parameter is that empty circle, and then the rest of the model parameters is each arrow, right? And that defines the entire model. So then the joint distribution we can define as follows. So this model completely models the joint distribution because we can break this out into p x given y and py, which are the two things that we're storing, right? And then just this this product is just oh, this is actually really important. It's and we're multiplying. We're representing p of x given y by making this independence assumption by saying each element in x is independent and is only conditioned on y. So we're saying this replaces this, right? Which is that naive independence assumption. So you might already be thinking, why is this useful, right? Why would you want to model the joint distribution this way? What can you do with those parameters that makes this particular formulation useful? So first, it's compact. We don't have a 2 to the x complexity model, right? We store a lot fewer values because of that independence assumption, right? Where we're not modeling the complete p of x given y possibility. We're treating each one independently. That's a far fewer parameters that we have to store. So the representation is very compact. And then using those parameters that we've stored, it's actually really easy to compute any quantity. And we'll show how that happens in the next few slides through examples here. And then also the model components that we need to store, so p of x and p of x given y, those themselves are also very easy to estimate given some data set, right? So and we'll talk about how we learn those parameters, but it's very easy. And then from there, it's easy to sample because, again, it's easy to compute any quantity. And again, because this is a generative model, it's very easy to deal with missing values because we can just marginalize them out, right? So this framework really gives us a lot of options for us to play with. Yeah.
I guess I'm still kind of confused on why it's more compact. With learning each one at a time. So that's how you say.
Yeah. So for example, taking the spam or ham example. So see how here for the word spam, we had to learn every single probability for 0, 0, 1, 0, 0, 1, and 1, 1. So that's 4, right? But here instead, we just learn x given spam, that's 1, and then x given spam separately. So this is a bad example because this is 2. But imagine if you have 3, right? Because we're kind of treating each of these independently, we don't have to cover every single possible combination. We just care about each x with respect to each y. Yeah, yeah. I should have had, it makes more sense if you do it with 3 columns, but you can't fit it on the slide if you do it 3 columns because it's 8 per. You need 16 rows, right? But you can kind of see that. Yeah. Any other questions so far? Cool. All right. So let's go through some examples, and you'll see why this is so useful and why this is so cool. Okay, so all right, so let's deal with this example model. Then let me flip my slides here. Yep. Okay. So we have an example learned model. So we're kind of ignoring the learning part for now. We're just assuming that we have this perfect model. So each xt is binary. This is the same thing we saw before, but these are the model parameters, right? So first we have x conditioned on y. So given that y is spam, what's the probability that x1 is homework, 0.2, not conditioned on not, 0.6, and then probability of winner conditioned on spam, 0.5, 0.1, etc. Right? So assume that this is learned. We'll talk about how we come up with these numbers later. And then also we have just py, right? So in our data set, what's the probability that y is spam is 0.7, and what's the probability that y is not? I don't know why they put not here. I like spam or ham because that like rhymes, right? But anyways, spam or not, 0.7 and 0.3. So again, because these are just the values that we're storing, model complexity is linear now with respect to the length of x instead of exponential. So instead of having to cover every single combination, we're treating each x element independently. And so you can imagine, we just add a column to this table every time there's new x. It doesn't increase in the number of rows, right? Any questions about this example model? Yeah. Yeah, that's the independence assumption, right? Mm-hmm. Any other questions? Well, yeah, that's the assumption. Yeah, sure. If we assume that they were correlated, then you would want x in the conditional here, right? Because you would say x1 depends on the whatever x2 is, then it would need to come after, like it would need to be x conditioned on y and x2. Yeah.
This assumption could also maybe be like regular. Like you consider all combinations.
So whenever I think regularization, it's like to prevent overfitting, right? So this is just more of a naive assumption so that our model like doesn't explode, essentially, right? Does it help with generalization? Depends on the task, right? Like it depends on whether this assumption is correct, right? And for a lot of cases, it's not. So you need to add some other dependencies, but yeah. Any other questions? Okay. So, yes. All right, so let's talk about how we would make a prediction given this model, right? So having the model is all fine, but we want to make our like traditional inference, right? We want to say, what's the probability of y given some x? And using some really basic probability definitions, first we have the definition of conditional probability, right? Where we have px comma y over px. And then we use the Bayes rule, right? To get down to break up the joint probability into this probability of x given y times probability of y, and that over p of x. Yeah, and then we have, so from there to there was Bayes' rule. And then from Bayes' rule to here, we have our naive Bayes assumption, right? Where we're assuming that each x is kind of independent, and each element of x is just conditioned on y, and not any of the other x values, right? So now we're just replacing p of x given y with this multiplication. And then finally, we can show that this is just proportional to this, because we don't really care about p of x, because x is given in our case. So we don't really care about this bottom term. So we can show that this is proportional to this expression. And you'll notice that both of these elements are elements that are already in our lookup table, are already model parameters of our naive Bayes model. Okay, so this whole task of predicting y given x just becomes two lookup table lookups, right? So it's very easy to compute that original prediction using these two parameters. Okay, so I mean, we can do the math, but I don't think I need to sell you on the fact that the math works. Although it is really interesting that given these kind of parameters. And kind of the intuition here is almost kind of difficult to build, right? Because we're so used to seeing y given x that when we see probability of y being 1 is 0.3, probability of observing some x given y is 0.05, and then probability of -1 is 0.7, probability of seeing x, given some negative y equals -1 is 0.0001. But when you do the math out with that, we can see that probability that y is 1 given x is like 0.96, right? So if you kind of stare at that a little bit, it's a little hard to build intuition for me, anyways, when I was learning this, because I hadn't really seen these type of conditional probabilities before. But the math does check out, obviously, because, again, this definition that we had down below, and the more you stare at it, the more it might make sense. Yeah?
The proportionality thing is saying, like, because for the probability of y given x, we only care about that as far as, like, figuring out what maximizes that, so now we're just trying to maximize the
Yeah, that, and we can just sum over all x's, right? We can just softmax it afterwards, right? So that's just, yeah, we can just softmax afterwards instead of actually calculating out what p of x is. Yeah. Did you have a question? That was your question? Okay, great. Any other questions? All right. So, okay. So that's our kind of traditional prediction task. Let's do something interesting. So a second example is what if we want to compute probability of x1 conditioned on the rest of the values of x and y. Does anyone want to guess? Yeah. The reasoning is correct, but the result is right. That's right. Right. Correct. So again, because of the independence assumption, because we're assuming that the each element of x is not conditioned on each other at all, this just collapses down to probability of x1 given y. It's an explicitly defined model component. Right. Yeah. I was like, what is that trying to say? Yes, it is an explicitly defined model component within our within the definition of a naive Bayes model. Okay. Another example. Oh. All right. Another example. What if we want to compute x conditioned on the rest of the values x to the d? And I'm not going to ask for a guess on this one, just because I don't want you to like talk that out, right? But in this case, again, we can just go through the full kind of definition, and at the end, we can always marginalize out the y, right? So even if y is nowhere in our data set, or nowhere in whatever our observed thing is, we can really just play with it and do probability arithmetic until we arrive at some form where it contains just the model parameters that we've learned, right? So y doesn't even need to be in the picture, nor does x, in the kind of questions that we ask with this type of a model. Oh, that's interesting. What slide is this? So Yisong kind of makes the argument here. Professor Yisong kind of talks about this, where whenever you do probability arithmetic, and whether it's on your homework or on your project, you should kind of always ask kind of sanity check questions, right? So probability is always between 0 and 1, right? So we should never get greater than 1 probability. So I guess the question he's asking here is, why can you kind of show that the numerator is smaller than the denominator without like doing the math, right? And the kind of what he goes into is that p of x given y is a product, right? And then at the bottom here, we have that same product, but it's missing one value. It's missing x, the first x element, right? And so when you think, why is that smaller than this? Because it has to be, because this whole expression was less than 1. We know that the probability of x1 given y has to be less than 1, right? And so because that's a superset of this value will always be larger because that additional element that you're multiplying, and remember, we need to break that out into the naive Bayes assumption, right? The sum of each of the individual elements, because it's missing that one element, and that one element is less than 1. You can kind of show that the top of this fraction will be less than the bottom of this fraction. The numerator will be less than the denominator. I think he's just kind of making the point that whenever you do probability arithmetic, if you need to double check that you're on the right path when you're like trying to prove something, just make sure that you're always ending up with some value that's less than 1, right? Because it needs to be, or nothing makes sense. Okay, any questions on these 3 examples? No, makes sense so far? It's kind of clever, honestly, right? You just store these 2 values and everything else collapses into these 2 values because of the naive Bayes assumption, because of the independence assumption. Okay, so we can also do this in matrix form, and this isn't that important. We're just including this here because this is a computer science course, and we're also always thinking about ways of doing this more quickly. But we can always represent our model parameters as matrices. O stands for observed, P stands for prior, and then we can just do matrix multiplication to do the same things that we've been doing so far, to make the predictions and calculate the parameters and such. So this is how you would parallelize, or CPUs have dedicated instructions for like matrix arithmetic, etc. Like Intel has an MKO library, like stuff like that. So we're just pointing out that you can do this in matrix form if you want to. Yeah. Okay. So again, kind of going back to this missing values point, because this is pretty important. Even if we never observe the second element of x, right? So we're used to doing y given x, right? But even if one of the numbers in that vector x is missing, we can still make a prediction because it's a generative model. So we can just, I think the example here is that x is 2-dimensional because here, so just assume that when we say x2 to the d, that's just x2. So even if we never observe, like this doesn't exist, it's not that winner's not in the text, we never checked, right? We don't have information in this, in this, we can still predict whether y equals spam based on just one of it, because again, we can marginalize out the second element of x with math, with probability arithmetic. So one of the points here is, in this case, we have 2 elements. So this is just 1 dimension. But what if d is 10,000, right? If d is like 10,000 and we're trying to predict y equals spam based on x1, like we have to sum over 9,999 values, right? So that can get pretty computationally expensive. So instead, we can take advantage of conditional independence to kind of alleviate a lot of that cost of adding up all of those like 9,999 values. So again, we have this from the previous slide where we're calculating probability of y given x1 by marginalizing out the rest of x, right? The rest of the elements in x by summing over them. We can actually use the definition of the naive Bayes assumption that we made to substitute. So again, we're summing over to the d. We're just replacing. What are we replacing? Yes, we're just replacing this sum we have at the top of that fraction with this expression because we're replacing that with that. And then we can swap the product and the sum because of the independence assumption that we made. I'm not going to go too far into that. And then finally, we get this expression at the end, so that we don't have to do this full sum. Because of the naive Bayes assumption we made, it collapses down into this very nice expression where, again, both of these are just elements in our lookup table. Okay. All right. He has these intuition slides here. He said he's going to skip this because it doesn't actually build intuition. I agree. So these are in the slides if you want to kind of explore that concept further. The idea of it marginalizing out to one, but you can come back to it in the slides. They're on the website, so you can go back on the PDF. All right, so let's make this final comparison again. Let's compare naive Bayes to logistic regression. So before we were doing a higher level comparison of generative models to discriminative models. Let's actually talk about just, yeah, I don't have too many more slides left here. So let's just talk about the comparison of naive Bayes with logistic regression. So again, with naive Bayes, we can really query any distribution, right? So y given x, x given y given just one element of x, one element of x given another element of x. Like we can be really flexible and pretty creative with the kind of queries that we're making. The training for naive Bayes is just counting the same way it was before, and we'll cover that in the next slide. We're kind of getting ahead of ourselves here. But we can just look at the training set and count how many times certain things happen, and that's all that's needed to train our naive Bayes model. But again, naive Bayes, because it's focused on modeling the complete joint distribution of p, x, comma, y, it's actually not optimized for classification accuracy. Right, so the optimization task isn't to improve predicting y given some x. Whereas for logistic regression, it can only query y given x, but it's very good at that one thing, right? So and the training requires this optimization procedure like gradient descent on whatever model that you're using to do your logistic regression. So computationally, potentially, it's more expensive. But because it's trained to minimize the log loss of p x given y, it does better. And that's not just like a theoretical thing, like empirically. This is a comparison of, so this table is all of these different models that exist. And then they counted how many times each model comes in first, second, third, fourth, or fifth against like some benchmark task, some benchmark classification task. And the point here is that naive Bayes, which is the only generative model on this list, always comes last, right? So it always comes 8th, 9th, or 10th compared to all the other models, all the other discriminative models that are on this table. So yeah, just to kind of drive home that like specifically for the discriminative task, if you're just doing classification, naive Bayes is probably not what you want to use, because it doesn't really care about that. It just wants to understand the joint distribution. Okay, so let's talk about training. So it's the same exact way we had before with our lookup table model. We're just trying to maximize the likelihood of the training set, right? Which is again minimizing the negative log likelihood. So because we're subject to this naive Bayes assumption, so the top half we already had with our lookup table, but because we're adding this naive Bayes assumption on top of the structure of p x comma y, we really only need to estimate py and p x given y. So instead of filling up that entire lookup table, we just need to fill up the tables that define these two parameters, and that part doesn't change. It's just counting, right? So for p of y, we just count the number of times spam documents are in the training set, which is very easy to do, right? We're just counting. Oh, I don't want to hit that. We're just counting the frequency of y in the training set, and then for this p of x given y, again, same exact thing, right? We just count the number of times. So if we're trying to do x is 1, we just count the number of times 1 and spam appear in the data set, and then we divide it by the number of times spam is in the data set, right? So again, we're just counting the frequency of these occurrences in our data set, and that's sufficient enough to fill up all the parameters in our naive Bayes model. Got it? Cool. All right, regularization. Back to the kind of topic that we were talking about before. So I don't know. This is interesting because, as an aside, again, this is Professor Ison's slides, but the way I've kind of discussed these regularization parameters in naive Bayes is as like smoothing. So if you want to Google this later, the words that you're looking for is like additive smoothing or like Laplace smoothing or like Lidstone smoothing. Those are 3 words for the same thing because that's how math is. You just have multiple names for the same thing. But I don't know. I don't really, I haven't really heard of this type of regularization being used in naive Bayes personally. Right? Yisang might know something that I don't. In fact, he probably does know something that I don't. But in my experience, in general, when we talk about regularizing naive Bayes, the intent is to not have zeros, right? So you don't want zeros in the bottom and you don't want zeros on top because that collapses everything down to 0 because you're always multiplying everything. So if you add like some constant, like we don't even have this uniform distribution here. If you just add some constant lambda, then you always prevent this fraction from becoming 0. It always kind of smoothens out to some non-zero value, right? So that's how I've seen this presented. But this slide also says, you can add pseudo counts in the same way that we did for our general massive lookup table generative model, where we just add some pseudo counts to the data set with some uniform distribution. Okay. Yes.
I guess I was wondering. So I understand why we don't want to have zeros in our p of x or p of y.
Mm-hmm.
But if we have something like if something that never shows up,
mm-hmm.
why do we want to model it?
Yeah. So
why not just remove it and don't care about it?
Yeah. That's a great question, and I think it has to do with the quality of your data set. Right, so it's kind of it's more of a practical concern where if your data set is small or it's not well represented, and you still want to, it's there, it just doesn't show up often enough or something like that, or more complex examples, that's kind of where you would get that from. Yeah, good question. Yeah. Any other questions? Okay. All right, sampling. Same exact way we did with our massive lookup table model, we can sample from a naive Bayes model. So in order to draw samples from p, x, comma, y, you first sample y, and then you would sample each xd, right? Right, and then you just feed that into the same naive Bayes assumption equation that we had before. Oh, it's all the way back here. We'll get to it on the next slide. But yeah, sampling doesn't change here. It's just that now that we have this naive Bayes assumption, the way you sample is different. You don't just sample from this massive lookup table. You sample y first, and then you sample each xd with respect to that y. One thing I do want to mention is on the graphical representation, you just follow the graph to generate your data, right? So you sample y first, because that's where we start, and then we sample x based on each y, conditioned on each y. All right, so we'll go through a sample example of this. So if we want to sample new data from this given naive Bayes model, we sample py first. So if, let's say we ran a random number generator between 0 and 1, we got 0.5, so we're going to set y to spam. So now that we know y equals spam, we're now going to sample x1 given y equals spam. So first sample y, that tells you which row you're in, right? And then when you want to sample x1, you sample according to that corresponding probability. And then same thing, right? So we've already established that y is spam based on sampling from this distribution. So then now, in order to sample x2, we sample from this distribution of this cell. One really useful thing about naive Bayes is that, again, x1 and x2 are independent. And so we can do this in any order. We can parallelize it. We can kind of make that more efficient because we don't have to go x1, then x2, then x3, then x4, right? We can just sample everything at once. So you can imagine kind of parallelizing that to multiple cores or something like that on a computer. Okay. All right, so again, because it's a generative model, we can sample whatever we want. So, wait, hold on. Oh, this is just another example. We're not going to get to that. Anyways, so but you can in fact sample more data this way, and this is just another example with different numbers. I was getting ahead of myself. All right, so as a quick recap of naive Bayes, that's really it. It's just it's a probabilistic generative model with that really strong independence assumption. One would say it's a naive independence assumption, which is why we call it naive Bayes. And we really like it because it's, again, a very compact representation. The model complexity scales linearly with the number of dimensions in your X. It's very easy to train. You just count how many times things happen in your data set. It's very easy to compute various probabilities, right? With just these two parameters that we memorize, we can really kind of do probability arithmetic to arrive at whatever we need to arrive at. And like we keep mentioning, this isn't the most accurate for just your standard supervised classification task. Other models do that better. But this model allows you to do things that you couldn't do before with discriminative models. All right. Any questions about naive Bayes? This is the last slide on naive Bayes. Yes? Oh, yeah. We'll get into that. So you need to do more because you can't just have a lookup table anymore, right? Because it's a continuous value. And so I have a slide on that. Yeah. Any other questions? Okay, cool. So naive Bayes is just a special case of a Bayesian network in that you can really draw that diagram any way you want and make any assumptions you want about the structure of this model, and we can learn it, right? So this is a model that Yisong made up on the spot, allegedly, where instead of just having one y, we have another y up here, right? And we can say that this y is conditioned on y2, and I don't know if this part's intentional, but is he saying that? Yeah, and he's saying that only the last element of x is conditioned on y2, right? This is not an actual model that's used. He's just kind of showing that you can really do whatever you want in terms of designing that model assumption, right? And so, again, even if you draw something crazy like that, your joint distribution definition just breaks out pretty cleanly, and you still arrive at a fairly reasonable thing. And then what you would have to do is you would have to learn each of those things, right, as a lookup table. So each element here would be a lookup table. Again, each arrow here would have to be a lookup table, right? So the point being, this is pretty flexible. So if you for some reason understand more things about your data or about your variables where you know some of these relationships to be true, you could set up your Bayesian network that way so that you can learn your task better, right? And that graph in particular is acyclic. It could be cyclic as well, although that gets complicated, I think. You might have to call that something else, but anyways, again, that graph can get fairly interesting. Okay, perfect. Okay, so we've talked about naive Bayes, and we've talked about just kind of a lookup table, and we're going to kind of briefly go over other probabilistic models. We're not going to go too deep into them. The only other probabilistic model that we're really going to dive into is HMMs, because they're highly relevant, especially for NLP before deep learnings took over. HMMs are still very useful, and I think it's a great example. So we are going to cover HMMs over 2 lectures after this lecture. So we'll really get to thoroughly know it. But we still want to kind of talk about what other things are possible with this kind of a structure. So first, we have Gaussian naive Bayes, where it has the same independent structure as naive Bayes, but it's continuous, right? So instead of using discrete values, now we have each probability function, each arrow is now a Gaussian instead of a discrete lookup table, because your variables are now continuous. So instead of this lookup table, you have some defined mean and standard deviation, which is all you need to define a Gaussian distribution, and then that's what defines each arrow going each way. And y itself, if y itself is also continuous, y itself could be also a mean and a standard deviation. And And then when you do sampling and stuff, it would just be like Gaussian sampling and things like that. So that's one way of dealing with continuous values. Let me make sure. Yeah, so instead of a Bernoulli probability, you get a Gaussian distribution. Yep. Okay. Next, hidden Markov models, which we're going to talk about thoroughly, so we're not going to talk about that too much. And this is also homework 6 and project 3, where we'll train this kind of a model on some text, and we'll try some generative things with that as well. It'll get pretty fun. But as you can kind of tell from this from the model diagram already, this is designed for sequences, right? So the way we have this problem set up, x1 is conditioned on y1, but y2 is conditioned on y1, and x2 is conditioned on y2, right? So it's kind of designed for problems where you have some sequence of inputs that and a sequence that you need to predict. Or again, we shouldn't really think about it that way. Just two sequences that you need to train over, right? That you need to model. We can also have something called a Gaussian mixture model. I want to point out that this is just probabilistic k-means, if you kind of squint at it, where each data point is associated with a membership to a Gaussian distribution. So not only are we modeling some k number of Gaussian distributions, we're also modeling the membership of some variable to which one of those Gaussian distributions. So the parameters that we're learning is this membership variable, where we say this variable is a member of which of these distributions, and then also we're learning the best distributions possible as well, right? So I think the next slide, yeah. So in a one-dimensional example with 3 Gaussians, right, maybe your data is structured this way, and your Gaussian distributions, here's the mean, here's the standard deviation, so we have these 3 Gaussians defined, and then we have this membership variable saying, your data point is a member of which one of these 3 hills, these 3 distributions. Yeah, mixture models are interesting. I'm actually doing some work with mixture density model. Anyways, sorry, that's off topic. All right, so the next thing is a topic model, also called a latent Dirichlet allocation. Dirichlet? Yes, Dirichlet. I'm not going to say that again. Anyways, topic models, which posits that documents can be represented as a mixture of topics, and then that topics can be represented as a mixture of words, right? So this is apparently called, I've never seen this before either. Apparently this is called plate notation, where you have some collection of documents, right? So we can say that a document is represented as a mixture of certain topics, right? So education or entertainment. I'm talking about news here. Like, let's assume that we have a corpus of news articles, right? So we can say that each document can be described as a mixture of certain topics, politics, sports, education, whatnot. And then that topics can be represented as a mixture of words, right? So those are the arrows that we're drawing inside this diagram. We have the m number of documents, and then each document has an n number of words, and we're kind of drawing these relationships between topics and the words. And the usefulness of setting up a problem this way, of setting up a model this way, is that this is how you can do text mining. This is how you mined like large corpuses of text before deep learning came and ruined everything, right? So the kind of interesting visualizations we can do is here you can describe what each topic is made up of words. So this is on the AP corpus. This is from the original kind of paper for this kind of work. So the model itself identifies topics as a collection of words, and then post hoc we can go in and say, oh, that looks like arts, that looks like budgets, that looks like children, and then also you can look at an individual document and you can say, what each word is a member of which topic, and then you can also describe documents as a collection of topics, as a mixture of topics, right? So this is kind of how text mining was done before deep learning came with their fancy transformers and kind of replaced everything. the previous example, if you watch Yisong's recording, because my lectures are unintelligible, he has a previous example on his slides where it's like it's an example on someone's blog where they use Sarah Palin's emails. And I didn't include that here because I don't know how they got Sarah Palin's emails. I don't assume that that's like a good data set. But if you're curious about that, I guess you can go look at Yisong's recording or like previous year slides. But it's the same thing, right? So you can describe topics as a collection of words, and you can analyze each document, see what words from each topic are coming, and documents themselves can be summarized as a mixture of topics. Yeah. All right, so deep generative models. So I made some of my own annotations on this slide. You can probably tell a bit of a bias in my opinion on this subject. But so deep generative models is, you can really think of it as a similar way, except this graph is like dense, like that graph notation becomes like impossibly dense, and somewhere in the deep model, like it has learned every single one of those like connections, right? So that's kind of how you can think of deep generative models. And so you can train these models to take in unlabeled images and just generate more of the similar, more of the similar, right? So you can feed it a bunch of images of, I think this particular example were lensed galaxies, right? So you can give it a bunch of examples of lensed galaxies, and it will kind of, in an unsupervised way, learn how to generate more allegedly lensed galaxies, right? Or you can feed it images of volcanoes, and it'll learn to generate more images of volcanoes. And there's a few different architectures for doing this. The one that you're probably the most familiar with is a GAN, right? It's a generative adversarial network where you have some model generating, so you have one model generating images, and then you have another model that's trying to tell whether or not that image is real. And so you train both models at once, and so they start fighting each other, and therefore the generated images get really good, right? But kind of in this framework of what we've learned today, you can kind of assume that this generator model is learning this joint probability distribution, but in like the image space, which is really interesting. So if we have time, so the scheduling for after the HMM lectures is a little tricky because it depends on the availability of Dr. Mandrake. But if there is time, I might squeeze in one lecture here where Yisong has some slides talking about like advanced deep learning methods. So if we have time, we'll talk more about GANs as well. So my 2 cents on this, and I'm sure since these slides were made, generative models have gotten better and better and better. And so I'm sure you've heard discussions on this as well in terms of ethics and everything else. But in terms of science, like learn from unlabeled telescope imagery, generate new images. Now astronomers have more data. That is not how that works, right? The models are very good at showing what's realistic. The question that you should be asking, and Lucas harped on it during his advanced topic lecture too, is whether that's useful, whether that's like something you want, right? Whether that's something you need. So in this case, this is also like one of those Nature news articles, which I'm not a big fan of, where like the paper itself is great, but then like the article goes and says like this, you can do all this stuff. I'm like, no, all right, that nothing in the paper said that. Like you're just, as a science writer, you're like making those posits. But like kind of questionable as to how useful this generated data would be to an actual astronomer, right? Especially because these were like gravitationally lensed galaxies, and like if you're no. And then also like, yes, you can get a model to generate more images of volcanoes, but like why, right? What are you using it for? If it's purely for entertainment, fine, I get it, right? But as soon as you try to use that for something useful, there's a lot of questions that you need to answer before you convince me that what you're doing is correct, right? And I'm not being like, get off my lawn here, like I'm serious, right? Like there's genuine questions about what's useful and what's not that needs to be asked before using generative models. The other thing that we get a lot about is deepfakes, right? And so one example of this is you can just generate faces. So you can give a model like examples of celebrity faces, and it'll just generate more examples of it. There's other more questionable types of deepfakes where you can replace someone's face in a video with someone else's face. So you can give it a collection of someone's face pictures, and then you can give it a video and it will replace someone's like face in that video with that face, right? So again, problem here is not the technology, but the consent and the ethics, right? Like, did you have permission from the original video and the face that you're replacing? If yes, go for it. If it's your own face that you're replacing with, that's totally fine. As soon as you use someone else's face without their consent or without permission to use their data, that's where we run into problems, right? There are far more qualified people than me to talk about AI ethics. In fact, it should be a course. It should be a mandatory course for CS majors, in my opinion. But anyways. WaveNet is really interesting. It's a generative model where you just give it text and it generates spoken audio of that words. So spoken systems have existed forever now, right? And one way you did this was to have a voice actor sit in a studio and say out every single word and then have the computer stitch them together. That's usually how that worked. But instead, with the generative model, we can actually generate very realistic spoken voice of some given text. We can even do style transfer. So we can give it someone else's voice, and then we can tell the model, generate this text, but in the style of that person's voice, and then it'll do that. So if you've been on TikTok or YouTube recently and you've seen like these Biden-Trump jokes where they like have them like doing some script at each other, that's what you're seeing. Again, ethics, permission, consent, and all that. But that's kind of the technology. If you use like Siri or Google Assistant especially, that's what that's using, because this is research from DeepMind, which is a subsidiary of Google. So this is kind of what the Google Assistant technology works on, and you'll actually notice that their text-to-voice technology has gotten like a lot better from 10 years ago, or even like within the last 5 years, like it's gotten very realistic. There's even an example where like my phone actually will, if I press a button, it will call a restaurant for me, and it'll place a reservation by phone call. Like it'll speak to the other person on the line and like play. Not in my voice. Yeah, in the Google Assistant voice. That would be very impressive, actually, and probably unethical. But this is like a big Google thing where they will call the restaurant in the Google Assistant voice, and it'll say, "I'm the Google Assistant for this person. What are your availabilities?" And then it'll like negotiate with the other person on the line and like get a reasonable recommendation. So that's, again, the technology. It's actually a really big deal because, like, going back to ethics, is a big deal because initially when they announced this capability at a conference, it didn't disclose that it's an AI. So it never said, "I'm Google AI doing this." It just says, I'm a personal assistant for so-and-so, and I would like to place a reservation. And it was doing things like, it was intentionally including like, just a second. Like it was intentionally including these kind of speech patterns to convince the other person on the line that, that's a natural conversation. And they like demoed it live on stage at Google. So it was a big thing. But again, this generative models have allowed us to really push the boundaries on this kind of technology. Yeah.
What is the reason that for this improvement, like new architectures, more data, like more better hardware to train on more data, more temperature?
Yes. Yes, all of the above. Yeah. So we have far more data than ever to train our models on. We have come up with very clever architectures. You know how we like talked about in deep learning where CNNs and RNNs are kind of, we're adding assumptions, we're adding kind of priors to the architecture of the model so that it does the task better. We've like done that to the extreme here, where this is like expressly designed model to like be able to generate these kind of speech waveforms from given text. And the compute that we have to train these kind of models is like enormous, right? Incredible amounts of GPUs and TPUs, and to the degree that they're developing their own AI chips to just do this, right? TPUs, like Google has their own silicon just for this. Like that's how the Pixel phone, like the Tensor chip, one of the reasons they made their own chips instead of using Qualcomm chips is because they wanted to add in neural accelerators for these kind of models that run on your phone. So yeah, all of the above, essentially. It's almost like Bitcoin mining. Like back in the day, you used to mine Bitcoin on CPUs and then GPUs and then FPGAs and then ASICs, which is like a application-specific integrated circuit to make mining Bitcoin faster. same kind of hardware arrays is happening with AI right now. This is Professor Yisong's project where you can feed in. He has these kind of sports information technology projects, which are really cool because they're just fun to look at. But you can actually train a generative model on basketball data, and you can generate new games, right? You can kind of say, if the players are here and the ball is here, like, what does the pass look like and when do they shoot? You can kind of generate a game, like a synthetic game from some game data set, which is really interesting. Oh, these are animated. Yeah, look at that. Yeah, pretty cool. I have no idea what the actual figures are meaning, but they're generated from basketball data. Okay, so last slide. Just to recap, generative probabilistic models. They quantify uncertainty in the sense that they can tolerate missing values. You can just marginalize out whatever variable that you don't have, and so you can kind of quantify uncertainty that way. The model itself is a full summary of the data because it learns that full joint distribution. And you can fit the model parameters to the data. You can, in fact, use the model itself for inspection, right? Do some of these probabilities that you've learned make sense, right? With the data that you expected. However, with these models, they're not trained to optimize prediction accuracy, so they don't do better than discriminative models if you just ask it to do a specific task, right? But because these are generative models, you can generate new samples, you can ask questions that you couldn't previously with discriminative models, etc. So it's just one more model in your toolbox to kind of tackle problems with and to meet the challenges of various tasks with. Next two lectures, we have the probability recitation on Wednesday. So again, if you were kind of lost in some of the probability stuff, maybe go to that lecture just to catch up. Next two lectures will be on hidden Markov models, which is sequence modeling. We're going to talk a little bit about dynamic programming, which is fun and comes up in like coding interviews all the time, right? And then you're going to implement aspects of HMMs in the homework and in the next project, and you'll do some cool text projects with it. That's it. Thanks. We're on time this time. Woo!